good afternoon or good morning, depending on where you are in the world. Thank you for joining me here in Liverpool in the UK. My name is Joe Brindley. I'm from Gencoa Limited, and I'll be talking to you for the next 15 minutes or so about automated analysis of vacuum processes using artificial intelligence, or AI. So artificial intelligence, which is powered fundamentally by machine learning, has revolutionized the way we interpret and use and analyze data. It underpins many important things within our modern world, with applications in healthcare, such as for screening for cancer, advertising, which is why I've said for better or for worse, you have adverts now that are targeted for you based on your browsing habits. It's learned what you want to buy. In transport, such as with self-driving cars, and the security, such as automated fraud detection, where it's looking for patterns of, say, credit card usage, which would indicate fraud. So just elaborate on that, an example here with cancer screening. So the traditional approach would be to perform a very costly or invasive scan, perhaps based on a doctor's recommendation, which is then based on some patients' feelings. And then this scan would of course have to be interpreted manually by an expert in order to come to some sort of conclusion as to whether the patient has a tumour or not. Well, this approach can be replicated with an artificial intelligence to yield much faster outcomes. So rather than using an invasive scan, you can take biomarkers which are perhaps regularly monitored throughout the year, and these markers can be fed into a machine learning algorithm which is trained to try and detect whether these markers indicate whether the patient has a tumour or no tumour. And closer to home, Applied Materials, for example, are using machine learning to create AIs that are able to automatically, very quickly, detect whether semiconductor wafers have defects on them, where those defects are, and then action on those defects. So it's coming closer towards vacuum systems and vacuum processes day by day. But where are we now for vacuum processes in terms of sensing? To do machine learning and AI, we need sensory data. But we're in a good position. We have many sensors available on most vacuum systems. This is just a vacuum system from PVT, and the possibilities are quite large. You can have residual gas analysis using optics sensor. You always have information as to what your power supply is doing in terms of perhaps generating a plasma, voltage, current characteristics, impedance. You can measure plasma characteristics such as electron temperature, for instance, in situ. You can measure the temperature of various points, areas within your process. You can monitor the plasma itself in terms of its emission characteristics. It's the light emission. And even if you have RF power, you can analyze harmonics and fundamentals within your RF power signal. So we have a lot of sensory information available. But what do we do with it? Well, we look at things in isolation, but gathering such a large amount of data really limits what we can do manually with, let's say, expert interpretation, manually sifting through the data. So this is where machine learning comes in. So machine learning tools are developed now to the extent where they can be democratized. And what I mean by that is you don't necessarily have to be a lifelong expert in machine learning and data science to get some use out of them. I myself am not from a machine learning background, but the tools are available that allow me to train AIs and perform machine learning operations on vacuum process data. So, taking all these sensory informations that we have within the vacuum system, we can run that through a machine learning algorithm, generate an artificial intelligence that could possibly tell us things like the chamber condition. When do we want to perform maintenance on the chamber? What state is the process in? Things like automatic leak detection, detection of the environment in the chamber, monitoring the vacuum quality, and then perhaps hopefully being able to monitor what the material properties are as you're depositing them in real time. So the ones highlighted there in bold are two examples that I would like to talk about today. So the first one, AI-based leak detection. Now, current methods for leak detection can be slow and or invasive. So perhaps you pump down to your base pressure after minutes, hours, sometimes days even, to let's say -5 millibar or below. And then you have a look at your residual gases using some sort of residual gas analyzer. And perhaps you see that you have elevated nitrogen oxygen. Okay, it means I probably have an air leak. Or quite common is to do a rate of rise test, perhaps at a slightly higher pressure, but still after pumping for a reasonable time. But this is quite invasive. You have to stop the pump down, you have to close valves, you have to stop pumps, etc. in order to perform this rate of rise test. Can we, though, use gas partial pressure data during the pump down to train an AI using machine learning that is able to detect leaks much faster than this, so much shorter into the pump down time, and without intervention? So that's what I hope to demonstrate. So first of all, we need training data. If we're to train an algorithm, we need to give it some data to learn from. So what I've given here are partial pressures during a pump down from the system, and these partial pressures are generated using the optic sensor. So this was done using a small turbo pumping system, so I can create these curves, these pump down curves quite quickly because it doesn't take that long to pump down to base pressure. And I've varied quite a few things and labeled the data. So first of all, there's a variation of leak rate, either completely leak-free, which these are labeled as such, leak tight, or with some variation in leak rate. In addition to that, the time that the vacuum system is exposed to the atmosphere is varied to have some variation in water vapor content. And throughout the pump down, I'm recording total pressure and various partial pressures. And that gives you my data set. So for one instance of leak rate and exposure to atmosphere, I have one data set of these values, and in total I have 3,700 data sets. That's for each point along the pump down curve. So with this data, I can train an algorithm. Now the algorithm that I've used is what's called a SVM, or support vector machine. If you think about it in two-dimensional space here, so I'm just plotting OH and N2 during the pump down, and this is my training data for leaks, no leaks, various different instances. And what it's trying to do is find a division between these two data sets. So in two-dimensional space, it's quite easy to visualize. The algorithm automatically finds this division between the two data sets, between leaks and no leaks, and so you can automatically characterize the data as such. If you're thinking about it in three-dimensional space with three variables, then you have this plane in 3 dimensions. But because we're using 7 different variables here, this is a 7-dimensional plane. You can't visualize it. You can't really imagine it except through the mathematics. I'm not going to go through that. But this is what it's doing. So it's taking the training data, it's taking these 7 different variables, these different partial pressures and total pressures, running it through this 7th dimensional SVM algorithm, and based on the instantaneous value of any of these, of the combination of these partial pressures, it's telling you whether it thinks the chamber has a leak or no leak. So we can test this out, and I've tested this on another system, so trying to test the generality of the method. So it's on a larger system with a 0.1 meter cube volume, pumping speed of 1,000 litres per second nominal, and I've got 4 pump down curves here. 2 of them I've created a leak on the chamber, and 2 of them are leak tight effectively. And just by looking at the pump down curves here, you can't really establish just a trend by looking at the pressure as it comes down. This is where the algorithm comes in. So if we look here at the 2 cases where you have a leak in the chamber, what we were doing is every 5 seconds, each one of these dots on the plot, every 5 seconds the algorithm is looking at those 7 variables, those 7 partial pressures, and trying to determine if the chamber has a leak or not. So I should say that the default state for the algorithm is that there is a leak in the chamber, and effectively it's trying to prove that there is not a leak, trying to prove that it's leak tight. So when we start the algorithm, which is at 0.5 millibar, all the way through the pump down curve, it's saying, yes, the chamber has a leak. If you compare that to the case where the chamber is leak tight, then at a certain pressure, the algorithm is able to detect that the chamber is leak tight. And in one instance, this occurs at 6 to the minus 2 millibar. In another instance, this occurs at 3 to the minus 2 millibar. But we can say approximately that below 1 to the minus 2 millibar, the algorithm is able to instantaneously and using continuous data throughout the pump down tell you whether the chamber has a leak or not. So this is quite early within the pump down. It's quite a nice result that you're able to see if you have leak tightness within the chamber very early into the pump down curve. So the other application I'd like to talk about is AI-based analysis of optical emission spectra, or OES. So I'm going to talk about this quite quickly. Traditional methods of analysing and identifying what you have within this optical emission spectra can be quite confusing, because a single gas can give you many, many different emission lines. So this is an example here of just nitrogen and argon, and that's it. Many different emission lines. And if you try and match that just to a database, the software can tell you that you have multiple possibilities for each emission line. So how do you know what you have? This is usually where sort of expert interpretation comes in. You're using your knowledge to eliminate possibilities and come to some sort of logical conclusion. Can we do that using an AI? So this becomes even more complicated if you take, for instance, a series of spectra, a time series. So in this case here, every 1 second I'm capturing a spectra. In this case, using the optics gas analyzer, it could be from a different source. It could be a plasma spectrum, magnetron, plasma treater. But I'm taking a spectra every second for about 1,000 seconds, and even in this fairly short time, that's over nearly 2 million data points to analyze. How would you analyze that by eye? Very difficult. So we can, though, use an AI to analyze it automatically. So the only information I'm giving to the AI is an emission reference library, a big library of molecular and atomic emissions and this spectra. And I want the AI to extract some trends, some fundamental trends from the spectra, and I want it to identify what gases or species, metals, etc. Those trends represent. So the way you do it, you start with the spectra. You put it through a clustering algorithm. So what that does is it tries to reduce the data set into some fundamental trends. So here it's reduced it into 7 fundamental trends. And for each of those trends, they're referenced with an emission library. And then each trend is fitted to the library to try and see what it closely matches, what best matches. So based on that, you end up with some isolated trends and a gas identification for each one. I think what's important as well is that each identification has a confidence interval based on how closely it fits the whole library for that gas. So you've got more of a probabilistic way of looking at what's in your spectrum. So just in summary, you start with this very complex spectrum in time and in terms of wavelength, and translate it automatically with just the gas library into fundamental trends and what the gases are and a confidence of what that gas is. So there are many areas for exploration though still. I think fundamentally what will be interesting as we go forward with using these techniques is combining different sensors. So here there was just one single sensor in each case, but combining different data streams. So information from the power supply, information directly from the plasma, gas analysis. Combining all these together, and perhaps that will be able to give us enough information to train algorithms that can monitor things like material properties as they're deposited in real time. For instance, hardness, opacity, electrical resistance, etc. So in summary, machine learning tools are widely available and very capable, and there's an opportunity to exploit these within the vacuum coating industry. So this presentation has demonstrated its potential for use in leak detection and automated analysis of emission spectra. The future will involve combining many different sensors to analyze the performance of the whole vacuum process in real time. So thank you very much for your time. You can find out more information at gencoa.com, or please feel free to email me anytime. And I very much hope to see you all next year in Long Beach in person. Thank you very much.